Good afternoon, everyone. My name is Utsav Ratnatuladhar. I am a PhD student here at the Electrical and Computer Engineering Department at the Rochester Institute of Technology. Today, I am here to present my first virtual poster on my work titled A Deep Learning Framework to Estimate the Shear Modulus from Ultrasound Measured Displacement Field. Ultrasound elastography. Ultrasound elastography is a non-destructive evaluation method for the medical diagnosis. This requires solving inverse elasticity problem, which is the identification of modulus from the measured displacement fields. Problem with conventional method in this field is that they are computationally costly and they are not suitable for real time. So our proposed solution is a deep learning method which we would train in simulated data and which would be suitable for real-time elastography. So different kind of NDA techniques has been used for geological exploration, construction, quality control, material evaluation, as well as in the field of medical diagnosis. The conventional methods like equation error approach, the joint weighted approach, these kind of approaches require linear optimization, which require multiple iteration, which increases the computation cost. Recent advances in deep learning methods have shown like promises in in improving these kind of methods. With enough data, we can build a model that learns the hidden relationships from complex patterns in those data. And we can leverage this idea in the field of elastography for high performance result. So our methodology is a threefold. The first is the finite element simulation, which we propose it as a forward model. The deep learning model, which we say it as an inverse problem, and the phantom experiments. The forward simulation method is the one where we generate the displacement field using finite element simulation method. For this method, the inputs are the modulus spatial distribution, the tissue sample geometry, for example, the shapes, whether it can be a circular shape or irregular shape, and the boundary conditions. And this input is fed into our FEA simulation, and from which we get as our output as the displacement field in the x direction and the y direction. So this displacement field are our inputs, which is our generated data from the FE simulation. So as we can see here, the displacement field are in the values between 0 and 1, and their corresponding modulus distribution are in the value of 0.01 to 5, where 1 is the white background, and the values less than 1 are in blue color, which indicates the soft inclusion, and the values greater than 1 are in red color, which indicates the hard inclusions. So the deep learning method we propose here is a unit architecture which does image to image translation. So our displacement field in U direction is our input to the unit architecture from which we get the modulus value. Our modulus value, our predicted modulus value and the ground truth modulus value are optimized using the mean squared error loss function and other parameters. So that to talk about the training details, the loss function we have are the mean squared error. The evaluation metric we have is the mean absolute percentage error, which is a normalized version, which is like a normalized version of our MSE. And the optimizer we have is the ADAM optimizer. The next method we use is we collect experimental phantom data, which, which is used to mimic the tissues of the human body. So this elasticity QA ultrasound phantom CIRS 049 is the phantom that we use, which includes both the hard and soft inclusions from which we take the ultrasound images of displacement field and predict the modulus of elasticity using our deep learning model. So, in conclusion, we present a deep learning method to calculate the shear modulus distribution in elasticity. And the breakthrough work that we have here is that we show that using the finite simulated data, we can develop and we can evaluate a model, a deep learning model that is capable of predicting the shear modulus, not only from the simulated data, but also from the experimental phantom data, which means that we can use simulated data to train an deep learning model and apply that model in real world data and and have this similar kind of results. Thank you. If you have any questions regarding my work, please feel free to email me at ut3320@rit.edu. Thank you.